Welcome back. Today we take an incredibly important step from description to inference, and we begin to learn how to make decisions about the tools that we'll use to ask our questions within this context of inference. So far, we've taken the first two steps in the larger picture of statistical inquiry, that is, identifying our data set and then using exploratory data analysis, tools that help us get a first feel for the data by exposing their features using graphs and numbers. Our ultimate goal is inference, drawing reliable conclusions about the population based on what we've discovered in our sample. In order to really understand how inference works, though, we first need to talk about probability, because it's the underlying foundation for the methods of statistical inference. First, here is the general idea. As we all know, the way statistics works is that we use a sample to learn about the population from which it is drawn. Ideally, the sample should be random so that it is representative of the population. It is important to acknowledge, though, that this does not mean that all random samples are necessarily perfect. Random samples are still random, and therefore no random sample will be exactly the same as another. One random sample may give a fairly accurate representation of the population, while another random sample might be off purely due to chance. Unfortunately, when looking at a particular sample, which is what happens in practice, we will never know how much it differs from the population. This uncertainty is where probability comes into the picture. We use probability to quantify how much we expect random samples to vary. This gives us a way to draw conclusions about the population in the face of uncertainty that is generated by the use of a random sample. Suppose that we're interested in estimating the percentage of U.S. adults who favor the death penalty. In order to do so, we choose a random sample of 1,200 U.S. adults and ask their opinion, either in favor or against the death penalty. We find that 744 out of the 1,200, or 62%, are in favor. Here is a picture that illustrates what we've done and found in our example. Our goal here is to do inference, learn and draw conclusions about the opinions of the entire population of U.S. adults regarding the death penalty, based on the opinions of only 1,200 of them. Can we conclude that 62% of the population favors the death penalty? Another random sample could give a very different result. So we are uncertain. But since our sample is random, we know that our uncertainty is due to chance and not due to problems with how the sample was collected. So we can use probability to describe the likelihood that our sample is within a desired level of accuracy. For example, probability can answer the question, how likely is it that our sample estimate is no more than 3% from the true percentage of all U.S. adults who are in favor of the death penalty? The answer to this question, which we find using probability, is obviously going to have an important impact on the confidence we can attach to the inference step. In particular, if we find it quite unlikely that the sample percentage will be very different from the population percentage, then we have a lot of confidence that we can draw conclusions about the population based on the sample. So let's define probability a bit more carefully. Probability is a mathematical description of randomness and uncertainty. It's a way to measure or quantify uncertainty. Another way to think about probability is that it's the official name for chance. Probability is the likelihood of something happening, with the probability of an event telling us how likely it is that that event will occur. So what values can the probability of an event take, and what does the value tell us about the likelihood of the event occurring? The probability of an event ranges from 0 to 1. Let's start with the extremes, 0 and 1. A probability of 0 means that the event has 0 chance of happening. It will never occur. An event has a probability of 1 if it will occur for certain. In the middle, a probability of 1/2 indicates the event has a 50% chance of happening. In other words, the event is as likely to occur as not to occur. Any probability that is greater than 1/2 indicates that the event is more likely to occur than it is not to occur. And a probability that is below 1/2 indicates that the event is more likely not to occur than it is to occur. Many people prefer to express probability in percentages. Since all probabilities are decimals, each can be changed to an equivalent percentage. Thus, The latest principle is equivalent to saying the chance that an event will occur is between 0% and 100%. As you know, so far in this course, we've spent all of our time in the realm of descriptive statistics. Through our examination of frequency distributions, graphical representations of our variables, and calculations of center and spread, the goal has really been to describe and summarize our data. The rest of the course will focus on inferential statistics. In addition to describing data, this very powerful tool allows us to directly test our hypothesis by evaluating, based on a sample, our research question, with the goal of generalizing the results to the larger population. To do this, we will be using probability to determine if what we observe in our sample is meaningful that is in a statistical sense, or whether what we observe is likely due to chance. To better understand the relationship between sample and population, let's consider two simple examples. Here I show you the distribution of blood types in the U.S. population. You can see that common blood types include type A and type O, with less common blood types including AB and B. Let's assume now that we take a sample of 500 people in the United States, record their blood type, and display the sample results. If you look carefully, you'll notice that the percentages of each blood type from our sample is slightly different than that of the population percentages. But I'm sure that this doesn't surprise you, right? I mean, since we took a sample of just 500 individuals, we can't expect that our sample will behave exactly like the population. But if the sample is random, as it was, we expect to get results which are not that far from the population, as we did. If we took yet another sample of size 500, we again get sample results that are slightly different from the population figures, and also different from what we got in the first sample. This very intuitive idea that sample results change from sample to sample is called sampling variability. Here is another example based on heights among the population of all adult males. As you can see, it follows a normal distribution with a mean of 69 inches and a standard deviation of 2.8 inches. Next, assume that a sample of 200 males was chosen and their heights were recorded. Here are the sample results, here in sample 1. The sample mean is 68.7 inches and the sample standard deviation is 2.95 inches. Again, note that the sample results are slightly different from the population. The histogram we got resembles the normal distribution, but not as fine, and also the sample mean and standard deviation are slightly different from the population mean and standard deviation. Let's take another sample of 200 males, displayed here in sample 2. The sample mean is 69.065 inches, and the sample standard deviation is 2.659 inches. Again, as in the example based on blood types, we see the idea of sampling variability. While the sample results are pretty close to the population, they're slightly different from the results we found in the first sample. In both of these examples, we have numbers that describe the population and numbers that describe the sample. A parameter is a number that describes the population, and a statistic is a number that is computed from the sample. Parameters are usually unknown because it is impractical or even impossible to know exactly what values a variable takes for every member of the population. Statistics are computed from the sample and vary from sample to sample due to sampling variability. The big idea behind making inferences about a population from a sample is that just like making distributions based on individual variables, theoretically, we can also create distributions for means or proportions taken from multiple random samples drawn from the population. Suppose next we selected 30 separate random samples rather than only 2, and that those 30 random samples each have 500 individuals drawn from the population of U.S. adults. For those 30 random samples, we measure the length of each person's right foot. Let's say that for our first sample, the sample mean is 10 inches. We could create a bar graph and plot that mean for our first sample on the graph. If our second sample had a right foot mean of 9 inches, we'd add that to the graph. As we continue to plot the mean foot length of each random sample, a pattern would begin to emerge. Notice how there are more sample means at 10 inches than any other length. Notice also how as the length becomes larger or smaller, there are fewer and fewer sample means. This is a characteristic of a sampling distribution, whether we are measuring the mean of a quantitative variable or the proportion of a categorical variable, or any other sample statistic. That is, as we draw more and more samples, the distribution of the sample statistics will become more and more normally distributed. This result is known as the central limit theorem, because as long as we draw adequately large samples from the population, and an adequately large number of samples, the distribution of those sample statistics, whether a mean, proportion, standard deviation, or any other statistic, will be normally distributed. Although, as you know, we ultimately rely on only one sample, if that sample is representative of the larger population, inferential statistical tests allow us to estimate, with different levels of certainty, the parameter for the entire population. This idea is the foundation for each of the inferential tools that you'll be using to answer your research question. I will begin to talk about inferential statistics by describing the steps involved in hypothesis testing. Hypothesis testing is used when we need to make decisions concerning populations on the basis of only sample information. A variety of statistical tests are used to arrive at these decisions: analysis of variance, chi-square tests of independence, etc. But they all include the same basic steps. These steps include specifying the null and alternate hypotheses, choosing a sample, assessing the evidence, and drawing conclusions. Statistical hypothesis testing is defined as assessing evidence provided by the data in favor of or against each hypothesis about the population. To provide an example of hypothesis testing, I'm going to use the NESARC data to evaluate whether or not there is an association between a diagnosis of major depression and how much a person smokes. Let's move through the example using the 4 steps: specifying the null and alternate hypotheses, choosing a sample, assessing the evidence, and drawing conclusions. First, there are 2 opposing hypotheses for this question. The null hypothesis, commonly shown as an H subscript 0, is that there is no difference in smoking quantity between people with and without depression. The alternate hypothesis, shown as H subscript A, is that there is a difference in smoking quantity between people with and without depression. The first hypothesis, also known as the null hypothesis, basically says nothing special is going on between depression and smoking. In other words, that they are unrelated to one another. The second hypothesis, also known as the alternate hypothesis, says that there is a relationship and allows that the difference in smoking between those individuals with and without depression could be positive or negative. That is, individuals with depression may smoke more than individuals without depression, or they may smoke less. After stating the null and alternate hypothesis, we need to choose a sample. I choose the NESARC as I'm interested in evaluating these hypotheses only among individuals who are smokers and who are younger rather than older adults. I further subset the sample to include individuals that are 1, current daily smokers, that is, smoked every day in the month prior to the survey, and 2, are age 18 to 25. This sample, N equal to 1,320, showed the following. Young adult daily smokers with depression smoked an average of 13.9 cigarettes per day, with a standard deviation of 9.2 cigarettes. Young adult daily smokers without depression smoked an average of 13.2 cigarettes per day, with a standard deviation of 8.5 cigarettes. While it is true that 13.9 cigarettes per day are more than 13.2 cigarettes per day, It's not at all clear that this is a large enough difference to reject the null hypothesis and to say that smokers with depression smoke more than smokers without depression. So now we need to assess the evidence. In order to determine whether the data provides strong enough evidence against the null hypothesis, that is, against the claim that there is no relationship between smoking and depression, we really need to ask ourselves, how surprising or rare is it to get a difference of 0.7 cigarettes smoked per day between our two groups, that is, those with depression and those without, assuming that the null hypothesis is true, that is, there is no relationship between smoking and depression. This is the step where we calculate how likely it is to get data like this when the null hypothesis is true. In a sense, this is really the heart of the process, since we draw our conclusions based on this probability estimate. So jumping to the punchline, it turns out that the probability that we'll get a difference of this size in the mean number of cigarettes smoked in a random sample of 1,320 participants is roughly 0.17, or 17%. We'll talk about how this gets calculated in the different statistical tests in later sessions. The important point at this stage is that it's this kind of evidence that we will be considering every time that we decide to accept or reject the null hypothesis. So how exactly do we use this probability to draw our conclusion? Again, we found that if the null hypothesis were true, that is, there is no association, there is a probability of 0.17, or 17%, of observing this size of a difference between smokers with and without depression. The translation of this 0.17 probability is that if we took 100 random samples from our population, we would be wrong 17 out of 100 times if we rejected the null hypothesis and said that there was a difference in smoking quantity for smokers with and without depression. Now we have to decide whether or not this is something that we feel comfortable about. Do we mind making a mistake and saying that there is a difference in smoking quantity 17 out of 100 times? Does this probability of 0.17 make what we're observing rare enough to feel confident about rejecting the null hypothesis? Well, I think that we can all agree that a probability of 0.50 would certainly not give us enough confidence to reject the null hypothesis, right? Because 0.50, or 50%, means that we would be right 50 out of 100 times and wrong 50 out of 100 times. Being wrong 17 of 100 times would make us far less likely to be wrong in rejecting the null hypothesis, but we would still be less certain than if the probability were even smaller. Basically, this is our decision when testing hypotheses. In order to make this decision, it would be nice to have some kind of guideline, would it not, about what is generally considered a surprising or rare enough finding that we have confidence in rejecting the null hypothesis. The reason for using an inferential test is to get a probability value, commonly called a p-value. The p-value provides an estimate of how often we would get the obtained result by chance if in fact the null hypothesis were true. In statistics, a result is called statistically significant if it is unlikely to have occurred by chance alone. If the p-value is small, that is less than 0.05, this suggests that it is likely, more than 95% likely, that the association of interest would be present following repeated samples drawn from the population, aka a sampling distribution. This cutoff exists, and because it is so important, it has a special name. It's called the significance level of the test, and is usually denoted by the Greek letter alpha. If the p-value is less than alpha, usually 0.05, then our findings are considered to be rare or surprising enough when the null hypothesis is true, and we say that the data provides significant evidence against the null hypothesis. If the p-value is greater than alpha, usually 0.05, then our data are not considered to be surprising enough when the null hypothesis is true, and we say that our data do not provide enough evidence to reject the null hypothesis, or equivalently, that the data do not provide enough evidence to accept the alternate hypothesis. If this probability is very small, then that means that it would be very surprising to get data like that observed if the null hypothesis were true. So again, a finding of p less than or equal to 0.05 means that our finding is statistically significant, that we can reject the null hypothesis and accept the alternate hypothesis. This p-value is also known as the type 1 error rate, since it denotes the number of times we would be wrong to reject the null hypothesis when it was true. Rejecting the null hypothesis when it is true is also called a type 1 error. If you'll recall from our example examining the association between depression and smoking among daily young adult smokers, the p-value was 0.17. Because 0.17 is greater than 0.05, we therefore have evidence supporting the null hypothesis. That is, that there's no association between depression and number of cigarettes smoked among daily young adult smokers. So let me change my question slightly so that you can see that the decisions you make about your sample and your variables can impact your findings and the conclusions that you draw. I'm still interested in the association between depression and smoking, but I decide that I do not want to limit myself only to daily smokers. That is, I'd like to consider a broader population of young adults, those that have smoked at all in the past year, whether daily or more irregularly. The size of this sample in the NESARC is 1,706. With this sample, I find that young adults with depression smoked an average of 351.7 cigarettes per month, with a standard deviation of 300 cigarettes. Young adults without depression smoked an average of 313.5 cigarettes per month, with a standard deviation of 268.2 cigarettes. So the difference between young adults who've smoked in the past year with and without depression is 38.2 cigarettes per month, almost 2 packs. And my p-value is 0.0285, obviously less than 0.05. This means that the probability that we would get a difference of this size in the mean number of cigarettes smoked in a random sample of 1,706 participants is less than 3%, which of course is less than p.05. So in this case, we can reject the null hypothesis and say that young adult smokers with depression smoked significantly more cigarettes per month than young adult smokers without depression. If we look again at the number line of probabilities, we can translate this finding in the following way. If we reject the null hypothesis and say that there is a difference between the average number of cigarettes smoked per month among young adults with and without depression, we would be wrong fewer than 3 out of 100 times. We would be correct more than 97% of the time. Based on the standards of science, this is a level of certainty that gives us confidence in saying that there is a significant association between smoking and depression among current young adult smokers. Now you should have a good feel for the general process of hypothesis testing. In the 3 presentations that will follow, I'll be showing you how to test your own hypothesis. Although you will always be interpreting p-values, regardless of the inferential test that you use, to choose the appropriate statistical test depends on the type of explanatory and response variables that you have. You will not only be learning about the inferential tools themselves, but also when and how to use and interpret them. Stay tuned.